Hello, so in this video we're going to be talking about a specific type of model. We've already kind of seen this model, but I'm going to talk about it in much more detail because it's kind of a really nice model to start off with to kind of ease you in. And it's actually, really simple, but it's kind of flawed in one really vital way. And, we're going to talk about that in just a moment, at the end of the video maybe. And it's called the exponential model. Now, I've already spoken about the idea that actually we would expect we would expect populations kind of to follow some kind of exponential pattern. So in other words, we'd expect them to follow a pattern that kind of looks like this. So we start off at initial value for the population at a particular time. So we choose a time where we want to start looking at the population and see what happens after that point in time. And the population at that initial point in time is called n0, okay? Then as we change through time, our population, which is going to be called n of t, should vary in an exponential manner. So in other words, it should get bigger and bigger and bigger. It should sort of start off relatively slow, and then basically as it's fairly obvious as we get more people in our system, more people are then having kids and whatever, or more animals or whatever, and then we're sort of expecting all of those kids then to have animals. So basically, have kids as well. So basically, as more people are getting in our system, we're having more kids being produced. So therefore, we should expect it to grow like this. Okay, the similar kind of argument for the for the reduction in population as well. Okay, so this should be an exponential model, and it's sometimes called the Malthusian model because it was named after Robert Thomas Malthus, okay, who first proposed this. Okay, so the first kind of assumption that we make is, okay, what is our growth rate going to be? So remember, we've got dn by dt. dn by dt, our growth, a rate of change of our population, will be determined by the number of people that we've got in our population times by some growth rate. Okay, and that growth rate will be dependent on n. Okay, and the most logical growth rate, providing of course we're considering a closed system. Yeah, we are considering a closed system after all. So in other words, we've got a country where we've closed off, or a village or whatever, where we've closed off the borders. Nobody's allowed in or out. We're just basically considering the people that we've got in that system, and we're considering they don't change, they don't leave or enter the system. Okay, and that is fairly obviously just going to be birth minus death rates. Okay, that's kind of fairly logical. Yeah, I think I've spoken about that in the last video, that, if our population is growing, then that means that more people are being born than people that are dying. So if our population is growing, then therefore we would expect our growth rate to be positive. So more people being born than dying, so therefore our growth rate will be positive. Okay, and we're going to call this R, just for growth rate rather than having G. Okay, if our population is getting smaller, that means that more people are dying than being born. So therefore, D is going to be bigger than B. Okay, so this is now our growth rate. So in other words, we can just substitute this back in here. So we get dn by dt equals n times r. Okay, or r times n, if you want to write it like that. That's how we normally write it, capital sort of alphabetical order. Okay, so basically what this model assumes is that we have a constant growth rate. Okay, and that growth rate will be determined by the amount of people being born and people that are dying, and that kind of makes sense. Okay, this is our growth rate here. I'm assuming it's a constant growth rate. Okay, and this is just our population size, and this is how our population is changing over time. Okay, so therefore, if we take the logarithm, basically this is an ODE. Okay, this is an ordinary differential equation. And so we can solve this ordinary differential equation. I was getting a bit far ahead of myself. This is an ordinary differential equation. And if you go back to my first video in this whole series, we formed our model. This is our model. We've identified what the problem is. We want to model our population. Okay. The next step is then to kind of introduce our parameters and model our parameters. This is what we've got here. Okay, this is our parameter, and our growth and our population, and how our population changes over time. Those are our parameters and variables. And so therefore now we've got our model. This is our model here, and we want to try and solve that model. And it's an ODE, so therefore this is the next step. We want to try and solve it. Now, how are you going to solve something like this? Well, I have done a series of videos on ODEs, so maybe if you don't quite follow this, you might be worth going and have a look at those videos. But essentially what we try and do is get everything involving n. We treat this dn by dt as a fraction. Now, strictly speaking, it's not a fraction, but the way that it works, it can be treated as a fraction. That's a really useful technique that you can do whenever you see a derivative like this. Okay, so we get everything involving n on one side and everything involving t, or a constant, on the other side. Okay, it doesn't matter. So in this case, r is constant, so it doesn't matter where we put the r, right? Whether we put it on the left or the right. So watch. So basically, I'm going to divide by n. I'm going to divide by n. So I'm going to have, well, I'm going to have dn by dt equals rn. Right, dn by dt equals rn. That's just what I've got there. I'm going to then divide by n. So if I divide by n here, then I'm also going to have to divide by n here. Okay, so therefore this just goes to 1, so this cancels. Okay, well look, I've still got a dt on the bottom here. So if I multiply by dt, then I'm also going to have to multiply by dt here. Okay, so this dt kind of goes away there. That just reduces to 1. So let's just write that out again, dn. And I've got rdt. And then I just integrate both sides. I just integrate both sides, and you know, this is just the way that works. This is something called separating variables. Okay, assuming of course that n is not equal to 0, that we can't have a population of 0. Because of course, if we have a population of 0, this fraction here is going to become 1 over 0, which will be infinity, which we can't have. So basically, we just assume the main fundamental assumption that we make here is that our population can't be 0. Okay, so let's solve this. So what's the integral of 1 over n? Well, the integral of 1 over n is going to be the logarithm of n. Yeah, the logarithm of n. And what's the integral of r with respect to t? It's going to be, well, there's no t in there at the moment, so it's effectively just saying what's the integral of a constant. So it's going to be rt, yeah, because if we differentiate this, we're going to get r back, yeah. And there's also going to be a constant of integration on both sides, but we tend to just combine the constant of integration into 1. The reason why is because there should be a constant of integration here as well, but if we move it over here, you know, we're going to end up with, let's say actually this is d. So this is a constant integration d. Okay, we're going to move it over here. So this is going to become minus d here. Okay, so it's going to become c minus d. Well, that's still going to be a constant. Yeah, it's just going to be two constants take away each other, so it's still going to be a constant there. So we just write it in one form over here. All right. So this is now the solution to our model dn by dt equals rn. Okay. Well, now if we just do a little bit of rearranging, now, well, actually, the thing which we want to determine, is what is our c here? What is this constant of integration? Okay, we know what n is. That's just our population. We know what r is. That's our growth rate. And we know what t is. That's just time. So what is c? What is the constant of integration? And that's normally given by some initial conditions. And the initial condition, which we normally know, is what is the population at the beginning of our system. So in other words, at time zero, what is our population? And we call that population n0. Or another way of writing that, n, our population at time 0, because of course n of t, you know, we've got n of t. So our population at time 0, so in other words, when t0 equals 0, yeah, because that's all time 0 is. It's just when our time is 0, okay, we're going to end up with, so when time is 0, we're going to end up with a population, and we're going to call that n0. So in other words, n of 0, neat way of writing that, n of 0 is n0. Those two things are exactly equivalent. So all this is saying is that at the beginning of the time period that we're considering, so at time 0, our population is going to be given by n0. So it's just going to be some number. Okay. Now if we use, this is what's known as an initial condition. So when we put t equals 0 into here, what do we end up with? Well, we're going to end up with log of n0, yeah, n of 0, because of course this is log of n. Strictly speaking, n is dependent on t, yeah. So if we put log of n0 is equal to r times 0, right? So that just disappears, yeah, because anything times 0 is just 0, is equal to c, okay. And I've told you. Okay, let's just rearrange this. So in other words, we end up with c equals, well, what's n of 0? N of 0 is just n0, right? I've just use this thing up here. So this is actually n0 in here. Yeah. So in other words, log of n0 is equal to c. So now I've got an expression for c. I can now plug this back into here. So I end up with log of n of t. So log of n is equal to rt plus c, which I've just shown you, is log of n0 plus log of n0. Okay, so this is this thing. Now I can do a bit of rearranging. Okay, because, look, if I just take this log of n0 over here, okay, I will end up with log of n minus log of n naught equals RT. You happy? Okay, well, by log laws, when we have two logs subtract each other, I can just condense that down into the argument, if you like, in the two logs. So this n and this n naught, those are the arguments. Okay, divided by each other. So log of n subtract log of n naught is going to be the same as log of n over n naught. Yeah, and that comes from kind of power laws. You can see that from power laws. Okay, and that's equal to RT. Okay, so now I can do even more rearranging. This log, this is a natural logarithm. Okay, not very nice. So let's just get n over n of n naught on its own like that. And let's take the exponential of both sides. Okay, so in other words, this is basically saying what power do I have to raise e to get n over n naught, and that's equal to RT. So therefore, if I just rearrange this as e to the RT. Yeah, and now if I just multiply through by n naught, that implies that n is equal to n naught e to the RT. And if you remember in the last video, that is what I was kind of using in the last video. So I kind of introduced the old idea with behind kind of where that, you know, the idea why that kind of made sense in the last video, but this is actually the derivation of where that came from. All right, but this actually is flawed in one really, really vital way. Okay, because at the moment, this model here is basically saying that my populations, this is n, this is t, my population can keep growing, so it starts at n naught, and it can keep growing exponentially in an infinite manner. So in other words, it will basically become asymptotic. It will basically grow infinitely. Okay, as we go through time, basically what it's saying is my population will grow infinitely. But fairly obviously, that can't happen, can it? That cannot happen. Because otherwise, you know, you're going to end up with an infinite-sized population. Well, there's not an infinite amount of space in the world. There's only a finite amount of space. Okay, so basically what actually tends to happen is if a population is really successful, in other words, the growth rate is growing sufficiently large, the population is sufficiently successful, what actually tends to happen is this, is that the population, you end up with an exponential growth, but then what happens is after a certain amount of time, it then starts to level off. Okay, starts to level off because there's only a finite amount of resources. I mean, if you think about it, there's only a finite amount of space. There's also only a finite amount of resources. There's only a finite amount of food and water, for example, in the world that a population can eat upon. So if a population gets large, if a population gets really, really large, then it's effectively going to be competing for resources. Okay, it's going to be competing for food and for water. Yeah? If a population gets too large. So effectively, what you would expect to happen is that a population gets sufficiently large enough, it will actually start to level off. Yeah, it cannot, literally, it's reached saturation point. It cannot take in any more people into that population. Okay. And so the population must level off. And the point where that population levels off, this kind of whole idea is known as a carrying capacity. Carrying capacity. I like to think of it as a train. Okay, a train can only take so many people. A train can only carry so many people. Before then, it reaches the point where it says, no, I can't take any more people on board, and therefore it's at its carrying capacity. And it's exactly the same idea with a system. Yeah, with a system of population like this, with a country or whatever. It reaches its carrying capacity. We normally give that carrying capacity the letter K. Yes, that's what we call K there. Okay.